This is the topic of anti-invar and invar. Okay, I write anti-invar first and not just invar because it turns out it's a 100-year-old problem, the invar problem, but it turns out that the anti-invar is a solution of the invar problem to a certain extent. So that's why I put anti-invar in the beginning of that. Now, so the problem goes back to a very, very long time, to the second half of the 19th century, actually. And the problem starts out with somewhere in France, where the French army had problems with their artillery. They'd fire the guns, and the guns would expand, and after a few fires, it wouldn't fire properly. So they had to get around this problem. And so a lot of metallurgy started there. They did all sorts of things. They made alloys of all sorts of kinds and things. And they found all sorts of new things as well. For example, in one kind, they alloyed iron with nickel or some other material. I don't know what it was right now, but what happened was that they have it at room temperature after the alloying, and then they take this down to solid carbon dioxide temperatures, what they had at that time, to get as cold as possible, and then take it back up to room temperature, and then suddenly they realized what was non-magnetic at room temperature became ferromagnetic, holding magnets and things like that, of course, to it. And this was one of the first encounters of the martensitic transition, but nobody knew anything about it, of course, at that time. And then over the years, there are other problems actually also. There were also other problems concerning structural stability. Not only the guns, but there was the meter standard. The meter standard was a platinum iridium alloy, and it was defined as the meter, and it was located somewhere in one of the rooms of the Eiffel Tower or someplace. Now, platinum iridium is very, very expensive, so not everybody can have one. And you had to go there, calibrate your sample or something like that, and then take it back. Platinum iridium, it has a very high melting temperature, and because it has a high melting temperature, it has a low coefficient of thermal expansion at room temperature. So that's why these materials were used for that purpose. Anyhow, from both of these motivations, both the standardization of the meter and to find a solution of expanding guns, people set out to research for new materials. This person is Charles-Édouard Guillaume. Started research, of course, with taking all sorts of materials, alloying them, and looking at the thermal expansion. He was a metrologist in Zurich at the time, and he was working on that topic, and he came through to a breakthrough when he prepared a series of iron-nickel alloys and found that at a particular composition, the thermal expansion would show the thermal expansion coefficient would be almost zero. And this is the composition, this one over here, this is the thermal expansion coefficient, this is the nickel concentration of iron nickel. So at about 65% iron, 35% nickel, they came to this composition. And you see he's measured this at 0 degrees and at 50 degrees centigrade. Those were the temperatures that were available or controllable or whatever. And he found this material. They named it Invar. It became a trademark. And in 1920, he got the Nobel Prize for this. So the thermal coefficient, the coefficient of thermal coefficient, as you know from your previous experiences, is defined like this. This alpha is the coefficient of thermal expansion. You have the length change equation here, so that if you heat the sample by delta T, the length will change by so much, assuming that alpha is constant, which is of course not, but okay, for room temperature purposes, it's constant enough. So the one of the first applications of this material was to do something that would show that it was really working and useful. The first sample where they measured, they were measuring thermal expansion. And so they took a sample, a very interesting sample, which was the Eiffel Tower itself, okay? And they wanted to know, the Eiffel Tower was newly built, and they wanted to know what the expansion properties of the Eiffel Tower were. What was happening when the temperatures were changing, because the whole thing is steel, it's huge, and what was going to happen when the temperature fluctuates between minus 20, minus 30 degrees, and I don't know how much in summer, maybe like here in Panjim. Yeah. So the idea was basically very simple. You take the Eiffel Tower first, and then you attach a wire to the bottom, to the second floor, and then the other end of the wire, this end of the wire, is attached to a recorder. This is an arm, and you have a drum here, a recording drum. So that if this wire is invar, and if the thermal expansion coefficient is 0, then this wire is not going to expand. The Eiffel Tower is going to expand, and you're going to have a recording here as this wire is constant and the tower is expanding. And indeed, they got very good data. So this is the daily movement. It's from 8 to 8 hours or something like that. You see, they record the temperature, how that varies, and this is the height of the tower. And you see it follows exactly the temperature. So you could use this for measuring these purposes. Quite an impressive experiment. So and then you have the movements of the tower under variable summer conditions. So it was a stormy week of August, September, or whatever, and you had here the variations in the temperature between 15 and 20 degrees almost, and then you have here storms coming in, rain pouring, the Eiffel Tower suddenly cooling down, sudden changes in the temperature. Sudden changes in the temperature made sudden changes also in the length. Now this was quite nice. We come to a point where we want to know why this is happening. Okay? Why does a regular, normal steel suddenly have a 0 thermal expansion coefficient? So this is what we want to understand in the course of this topic. This evolved into a problem. The problem is still being discussed. It is not a fully solved problem. It has magnetism in it, but there are still lots of controversial aspects to it. And one of the a new way of looking at it is to try to understand what the elements in these things, it's not too much, it's iron and nickel. What is the active element here? What is happening? Is this an alloy property? Is this an element property? So we start out by forgetting the INVAR problem at the moment, and we just look at our periodic table, okay? So if we look at the periodic system of the elements, you go from scandium to copper, and then these are the 4D and 5D elements over here. When you look at the structures of these elements, just the structures, you find that the 5Ds and the 6Ds all follow a certain pattern, especially at room temperature. So you find at the left you have the hexagonal close packed structures, then you have the body-centered structures coming out, and then again you have the hexagonal, and then you have FCC. This is how it sort of evolves when you go through the periodic system. When you look at the 3Ds also follow this up to chromium, but these three here, they deviate. This becomes a complex cubic, this becomes body-centered cubic, and this becomes hexagonal instead of FCC. And then in nickel and copper, everything is normal again. So something happens, and we say that these three elements have, at room temperature at least, the wrong crystal structure. They should be something else. What should they be? Manganese should be hexagonal. Iron should be hexagonal. And cobalt should be face-centered cubic. We don't encounter these. Of course, face-centered cubic exists at higher temperatures, but how is it that iron is going to be hexagonal and manganese is going to be hexagonal? Why are they so far away from what they're supposed to be? So then, instead of just looking at the room temperature structures, let's look at the structures as we vary the temperature. Some undergo phase transitions, so we call this theolotropy. Are there any questions in between or something like that? Somebody raise it. Okay. So we look at the allotropy in the 3D elements. Titanium, okay, it's hexagonal at low temperature, but it becomes body-centered cubic at high temperature. Scandium, it's not shown here, but it's all hexagonal. And then when you go to vanadium and chromium, you find the body-centered cubic stabilizing all throughout the temperature range. Vanadium is paramagnetic, and chromium has a nail temperature around 312 Kelvin. So you see that this BCC region opens up. When you come to manganese, you find 4 different structures. If you find 4 different structures, the thing that immediately comes into mind is that you have competing structures with very small energy differences, so that if you apply pressures, if you change the temperature, if I don't know, if you induce strain or something like that, one structure may change into the other structure. You have alpha manganese, which is the so-called A12 structure. It is a complex structure with about 56 atoms per unit cell or something like that. It's a cubic structure though. It's still cubic. And then you have the A13, which is beta manganese. That has 26 or 28, I'm not sure. So many atoms per unit cell. And then when you come to a higher temperature, you have Fcc manganese, face-centered cubic manganese. And if you yet go higher, you come to the body-centered cubic manganese. You come to our Häusler. Actually, it's the body-centered cubic manganese where our manganese, the environment of manganese is. Yeah, of course, it's not Häusler up here, but I mean, if you have a Häusler, then you have manganese in a body-centered cubic environment, or a face-centered cubic environment. But it doesn't matter. I mean, you're in some kind of a cubic environment over there. Okay. So this is the only element that has these very, very complex structures. When you go to iron, you have the BCC state. The BCC state, unlike the BCC state here, is not a is not a state stabilized just by what would you call it? Entropically, that is, it's not just the temperature which brings it to that state, it's also the magnetism. So if iron were not magnetic, it would have not been BCC. We'll see what it would have been. But anyhow, when it is BCC, then it has a Curie temperature which is located somewhere up here. And then we have Fcc iron, a region, where suddenly when the magnetism is lost, the BCC state is no longer stable. It goes into a more densely packed structure. And Fcc iron can be in an antiferromagnetic state with a Néel temperature somewhere around 70 Kelvin or so. That can be estimated. But it cannot only be antiferromagnetic, it can also be ferromagnetic, depending on the atomic volume. We'll go into that. When you go to higher temperatures, the BCC state recovers again. It's because it's a more open structure than the FCC, and it is expected that you would go into a more open structure at high temperatures. So what is actually happening is that you see that this BCC region is opening up and then it's narrowing down, and after this there is no body-centered cubic structure. After this, as of manganese, you see the face-centered cubic region opening. Still, when you come to cobalt, cobalt is hexagonal at low temperatures. When you go to high temperature, it becomes face-centered cubic. You can measure a Curie temperature of the face-centered cubic phase, which is up here, it's quite high. You cannot measure directly the Curie temperature of the hexagonal state because before reaching a Curie temperature, the structure changes and you come into the FCC state. Of course, then you have nickel, which is stable everywhere with a Curie temperature around 600 Kelvin, and then you have copper, which is not magnetic. So this is how this structure varies all throughout. Now we're going to be talking about anti-invar and invar, and this has iron in it. So first, it is important to understand iron. What is iron? What is iron doing? What are the characteristics of iron? And how these structural changes and things affect when they are incorporated in another alloy. How are these properties brought in? Now let's look at the phase diagram of iron. So we have lots of phase transitions here, okay? So we have the temperature dependence. That is the critical temperatures as a function of pressure. What happens when we vary the atomic volume in iron? That's why we're looking at the pressure. So we have here various phases. At zero pressure, as we had seen, we have here a BCC phase. This is the Curie temperature of BCC iron. And then we come into the FCC phase. And then here, this is also BCC iron, and then we go into the liquid phase. Historically, these were designated as alpha, gamma, and delta. There was also a beta phase. The beta phase was the non-magnetic BCC phase historically, because people didn't know, people thought that when you come to the Curie temperature and above the Curie temperature, when the magnetism vanished, they thought initially that was a new phase, so that was called the beta phase. So that's why beta is missing here. But then it was realized it was the same as the alpha phase, so beta was abolished. So we have alpha, gamma, and delta phases in metallurgical terms. So now, when we increase the pressure, what you see here immediately is that the close-packed structure stabilizes to lower temperatures. So this transition temperature here shifts further and further down. And here also, you find that it goes more and more upwards. So this gamma phase region expands when you apply pressure. The gamma stability range, which was this, at certain pressures becomes something like this here. If above a certain pressure, however, the gamma phase transforms to the so-called epsilon phase, and the epsilon phase that comes after delta because it was found after delta, the epsilon phase is hexagonal. So if you apply a high enough pressure, you come into the hexagonal state. Now, if you are at room temperature and apply pressure, you are in the body-centered cubic state, and then you cross a line at around 15 gigapascals, and then you come into the epsilon phase. If you want to return back into the alpha phase, there's this tremendous hysteresis here, and it's only when you come below this line over here do you get back into the alpha phase. These are designated as MS here and MS here in both cases. This is a mixed phase. It's like a martensitic transition undergoing, like in nickel titanium. You're applying a strain, you're inducing a martensitic transition. It's a martensitic-like transition going to the epsilon phase, and when you're coming back, you come through it with a hysteresis. Now, there are certain things that we can learn from this phase diagram. This tells us, okay, what's happening under pressure, good, but what have we learned so far? Extra, as more information. If you take this line over here, which is the transformation line between the FCC and the hexagonal state, okay, and you extrapolate this back to 0, you would see that a gamma FCC transition would occur at around this temperature over here, close to 500 Kelvin. Meaning that if it were possible to stabilize the epsilon state, it would have had a transition temperature of so much, and the epsilon phase would have been more stable with respect to the FCC phase. Same thing goes for BCC iron, that at zero pressure, the epsilon phase would have been the most stable phase if BCC were not magnetic. What stabilizes the BCC state is the magnetism. So if you take away the magnetism of the BCC state, it's not the FCC state that's stable, but it is the hexagonal state that it is stable. So what happens then? It is the magnetism that stabilizes the BCC state. And if we don't have magnetism, the hexagonal state is stable, and everything on the periodic table is better then. So we have ruthenium and osmium underneath iron. Both are hexagonal. And we can show, just by these simple arguments, that iron should have been hexagonal in the event if it were not magnetic. That's one thing we can learn from this phase diagram. The next is, what would happen if it were possible to go to negative pressures? That is, if we were able to expand the volume somehow. This is a body-centered cubic phase. It's stabilized purely entropically. and this is the BCC phase, which is stabilized by the magnetism. So if it were possible to open up the volume, or to increase the volume by applying negative pressure, hypothetically of course, then this line would have most probably closed in as such, so that the FCC phase would no longer be stable and only the delta phase would be there. So these are things that we can sort of acquire information on what is going on, what could be going on in iron under different conditions. Okay. Are there any questions up to here? Okay, now this is iron. Good. Now, iron is very versatile, especially when you put carbon into it. You get various kinds of steels. The question is, why can you put carbon into it? How does carbon go into it? What are the limits, and how does carbon go into all these different structures? Now, carbon comes in, let's say, we have the BCC state and the FCC state, and let's take a look and see what are the places where carbon go in. Now, carbon goes in here interstitially. It goes into octahedral voids, which are located at these positions shown by these open circles here. So in the BCC case, you have these octahedral voids here and these octahedral voids here. And when you look at this octahedral void, this should be less than this is a sort of a compressed octahedral void. And then we have the tetrahedral voids over here. In the FCC structure, the octahedron here lies in the middle and also in the corner. Now, the void radius in this case is so much, and we want to put in a carbon atom, which is so much. How will that fit in there? So the same thing goes for FCC iron. We see that we have a void radius, which is also smaller than the carbon covalent radius. Now, in this case, it can either go in here or it can go in here. If it were to go in here, it has to expand everything in all directions, which costs a lot of energy. So instead of doing that, if we put carbon in here, then it induces a strain in this direction here, that's in the vertical direction, so that it distorts the lattice. And when we put carbon in there, we have a body-centered tetragonal state. And the body-centered tetragonal state is nothing but the martensite. Okay? So that's how carbon goes in there, by forcing its way in at high temperatures when you've expanded the lattice, and you get the martensite. In the phase diagram, you have the FCC state here, and you have this here. Okay? So if you put a carbon atom in here, this has to expand in all three directions. It cannot expand in all three directions here, but it does expand in all three directions here. And the reason why it can expand in all three directions is going to be more evident when I show you more about the expansion properties of these materials and the anti-Invar effect. So, if we are sitting at a very, very, very low carbon concentration, and we put carbon into the thing, it is possible to dissolve a certain amount of carbon into this structure, into this void, so you get these things called the ferrites, okay? Ferritic steels. Ferritic steels means body-centered cubic steels. It's come to be known as, for example, you take iron chromium is a ferritic steel, okay? Any steel that remains in the body-centered cubic state. If you are in the austenite state, then you have this structure, And if you quench this very rapidly, then you will have carbon trapped in here, and you get a rest austenite. You have the Fcc state, so to speak, stabilized at low temperature. And these are known as the austenitic steels. So the austenitic steels are face-centered cubic, and the others are body-centered cubic. Now, then the austenitic steels, the typical ones you have in your kitchen. It's called the 1810 or whatever. It's an iron nickel chromium steel of some sort. And it's face-centered cubic. If you hold a magnet to your kitchen appliances, it should not attract. If it attracts, then it's not of good quality. Okay, it should be non-magnetic. The ferritic steels are ferromagnetic. So that's one way of distinguishing, more or less. It's not in all cases that austenitic steels are non-magnetic, but you can tell whether you have a ferritic steel or an austenitic steel. So, and then when you come into these regions, you have cementite and things like that. We'll talk about that later on. Now, we come to a point where we want to look at the thermal expansion properties. So we have here a plot of thermal expansion multiplied by the melting temperature over the temperature reduced to the melting point. The alpha Tm is therefore, when we write down that equation again, we have what? L equals L0, 1 plus alpha delta T, yeah? And if we consider the length variation from the lowest temperatures to the melting point, then this delta T would be the melting point minus practically 0. So that would be Tm. So this here would be alpha Tm. So that on this side we would have L minus L0 divided by L0. So this would be delta L over L. And this would be alpha Tm. Now, this is why we plot alpha Tm on that side and try to understand what the length change. So alpha Tm is basically the length change at the melting point. You see here that when you plot this alpha Tm for all these elements, you find that they all lie on this so-called general lattice expansion curve. So all cubic materials essentially expand by the same amount before they melt. They expand by about 3% before they melt. So be it if you have a high melting point, like in platinum or iridium or whatever, then when reduced to the melting temperature, it has the same property of another element which has a much lower temperature. So if you have a low melting point, you have a high thermal expansion. If you have a high melting point, you have a low thermal expansion. But if you consider that in this diagram, everything is the same. Almost everything. We have here this yellow is nickel. This black one is body-centered cubic iron. You see, they all look normal. They confine to all these things. But when you look at gamma iron, Fcc iron, and when you look at gamma manganese, that's Fcc manganese, these are tremendously anomalous, okay? You can measure the thermal expansion coefficient of gamma iron at high temperatures. You get practically no variation and a very high value. If you can also go to 1400 Kelvin where gamma manganese is stable, And by some X-ray, high temperature X-ray measurements, you can also make a measurement over there, and you get this value. This is gamma. If you put a little bit of copper into manganese, you can stabilize, you can open up the FCC region so that you can stabilize the FCC state to quite low temperatures. So this would be the manganese copper that you have. So this is more or less pure manganese, and this is all manganese copper, and this joins over here. This is basically then gamma manganese. So the question is now, what is going on? Why is the thermal expansion of gamma iron so, and why is it in manganese so? So these two materials show anomalies, as they did in the periodic system with their structures, also in their thermal properties. So the best way of looking at this is to do some measurements on these things. How can I go from gamma iron, which looks like this, to something more normal, like nickel? And since we're going to be dealing with INVAR, let's look at the thermal expansion properties of iron-nickel alloys, keeping this in mind as the general lattice expansion. This is a mess, okay? Now, this was done by an old PhD student of ours, the days when we were working with INVAR. He said, let's take these materials and measure their thermal expansions and see how they behave in the face-centered cubic state. This curve over here, this thick line, is our general lattice expansion. And we've plotted here again the reduced temperature dependence of alpha Tm. This is iron. That's gamma iron. Okay? This dotted line shows you what it would be if certain things are taken into consideration theoretically, but let's leave that alone for the moment. We just have measurements. We're looking only at measurements. We have gamma iron. This below here, it's BCC. Above here, it's also BCC, so we don't look at that. And then we start adding a little bit of nickel into it. The transitions from the FCC to BCC are shifted to lower temperature, and this also to lower temperature. And then we start increasing the amount of nickel. What is happening? We are gradually approaching the general lattice curve. But it's still anomalous. So iron itself, this iron itself, is carrying its anomalous behavior along with it into the alloy. So then we come to this composition here, and this composition here starts doing funny things. In fact, this one also. When you measure this, you see here that the thermal expansion coefficient, it lies firstly above this lattice curve, but then it crosses it. And then you come here to the INVAR composition, where the room temperature thermal expansion coefficient was 0, what Guillaume had measured, and you find that at high temperatures it conforms to the general lattice expansion, but when you go down in temperature, it suddenly does something funny, and it deviates from this general lattice expansion property. So these deviate positively, and these here, they deviate negatively. When we look in this panel, this is just a continuation. We didn't plot everything here because then it gets too complex. We have this repeated here, the 35, same curve. And then as you add more, this time it starts coming from below and merges with the curve of nickel, which conforms to the general lattice expansion property. above a certain composition of about 70% or something like that. And interestingly, that 70% is the composition which everybody talks about these days in thin films and this and that of permalloy. Okay? So these are all quite interesting coincidences. So there are two questions then. First of all, why are all of these above and why are all of these below and why do these cross? Okay? If we are, when we understand this, or if we're capable of understanding this, then we will have understood a lot more about what iron is basically doing there. So now we'll look at what theory has to say about this. In the late 1980s, computers grew, and the IBM at the T.J. Watson Center had this huge computer which had a capacity of my laptop now, okay? But that was in big rooms. And only a few people could use them. And there were several physicists over there which came out to the idea that saying that let's use this computer to make our calculations more complex. So what they were doing the so-called local density approximation calculations. And but for that, to be able to do the calculation, they had to assume some experimental values, fix it, and do like a calculation which results in an energy versus volume diagram. These were done in the earlier days, in fact in the 1970s and so, and these gave hints on the fact that Fcc iron and Fcc manganese were not like the other elements, but they showed some anomalies in their magnetic properties. So we're looking at electronic structures now. What determines an electronic structure? Which parameters do we have? We have the binding energy, we have the volume, and we have the magnetic moment. That's all we have, yeah? And that determines our electronic structure. Now we have three things to calculate. If it were two, it'd be okay. So the people came out with an idea to fix a magnetic moment to a certain value and then to do a calculation of the binding energy with respect to the volume. So then you go to a next moment, you fix it, and you do another calculation. Next one, another calculation. So you do a series of band calculations, which is of course very time consuming, and it requires a laptop, okay, today. But in those days, it required these huge computers. And then you get results which you can look at as three-dimensional. That is, you have at constant energy surfaces, and you have the energy and you have the magnetic moment. And from there, you can derive diagrams that look something like this. This is the binding energy diagram of Fcc iron. This is the Wigner-Zeitzel radius. That's nothing but the lattice parameter or the volume. It's connected. The Wigner-Zeitzel radius is proportional to the lattice constant, where here n you have the number of atoms per unit cell. In BCC it's 2, in FCC it's 4, and A is the lattice parameter. You look at certain states which you want to give in as input. One is the ferromagnetic state, and the other is the antiferromagnetic state, and perhaps a non-magnetic state. When you do that, what you find is that for the antiferromagnetic state, the binding energy follows a curve something like this. And the antiferromagnetic moment looks something like this. This here is the equilibrium volume. So under equilibrium conditions, the magnetic moment of the antiferromagnetic state or the non-magnetic state should be somewhere nearly zero. And then you redo the calculations for the ferromagnetic state. You find a binding energy curve where the minimum lies at a slightly higher value than the antiferromagnetic state. It crosses the antiferromagnetic state and follows a curve like this, so that you have a critical volume over here, or a critical Wigner-Zeitzel radius, below which the antiferromagnetic state is the most stable state, and above which the ferromagnetic state is the most stable state. The magnetic moment of the ferromagnetic state below this critical value is practically zero, and then you have stable solutions over here, which are referred to as a low spin state, and then it jumps up, and then you go into the high spin state. So the ferromagnetic state is not a unique state, but it has a low spin state and a high spin state. And under equilibrium conditions at very low temperatures, the antiferromagnetic state of Fcc iron should be the stable state. Okay. And as you go to higher volumes, you have the high spin state as a stable state. Now, before we go into any comparison with real systems, let's look at Fcc manganese and see what these people have done. Fcc manganese shows basically the same thing, except that in the range of the calculations here, it is shown that the antiferromagnetic state is of the lower state, is the lowest energy state. So Fcc manganese is antiferromagnetic. And then when you go to very, very, very high volumes, it is only then that the ferromagnetic state has a chance to be stabilized. So you really have to expand manganese before you can make it ferromagnetic, in contrast to iron, where you can play around with it. And that's why if you make thin films of iron, you can stabilize Fcc iron on copper substrates to a certain thickness. You can measure nail temperatures. You can measure the antiferromagnetic transition temperature. You can measure Curie temperatures. I'll be showing you those. But with manganese, you can never do this. People have tried this. People have tried a lot of stabilizing manganese films on substrates, but you can never find a substrate that has a large enough lattice parameter so that you can stabilize Fcc manganese epitaxially on a substrate, giving you ferromagnetic exchange. If you would, you'd be very rich. It has a very high moment, and ferromagnetic, it would be the strongest magnet in the world. Okay? So at this point, let's give a break. Then I will come into a few more of these diagrams for normal systems. I've just shown you two systems with anomalies, Fcc iron and Fcc manganese. We'll see how normal systems look like, and then we'll go back into the experiments and try to understand what the whole thing is all about. We are not at a point where I showed you Fcc iron and Fcc manganese, and they look similar, except the scales are quite different, yeah? The critical volume is somewhere over here. This is about 1015, that's millirydbergs per atom. In terms of electron volts, I think that's about 1 millielectron volt. Now, 1 electron volt is 11,000 Kelvin in terms of kT. So 10 millielectron volts are about 100 Kelvin, yeah? So, and 1 millielectron volt is 11 Kelvin. So, this is in the order of about, this is here, in the case of FCC iron, it's in the order of about 10 millielectron volts in hundreds of kelvins. So what happens is that by thermally heating and things, it is possible to actually go from an antiferromagnetic decoupled state or a low spin state to a high spin state within the thermal range. In the case of manganese, well, if the meeting point were here, this is just too huge. So if you have antiferromagnetic manganese, just by heating it, you don't get ferromagnetic manganese. But if you make an alloy, a compound, with a volume which is close to this, with a composition that has a volume close to this radius here, then all you have to do is heat it and cross this. So in the case of hoisters and things, you are very close to ferromagnetic transitions, like what we have in our shape memory alloys, yeah? We have manganese in a cubic environment, and by changing the temperature, we can easily cross from one state to another state, meaning that the energy difference is in the order of 10 millielectron volts or something like that. Now let's look at something normal. Normal was, as normal we define a material that shows a regular thermal expansion up to the melting point, yeah? BCC iron. You see here, everything is stable. The magnetic moment of BCC iron in the equilibrium state is about 2.2 mu B, which is reproduced in these calculations. In contrast to that, we have in the equilibrium state for manganese, you have no moment at very high values. You come to values about 4 Bohr magnetons, which is actually values that you observe when you measure the magnetic moment of hoistlers, of the manganese atom in the hoisters. It's in the order of 4 Bohr magnetons. So these calculations back in the 1980s, of course they've been improved, there are better calculations and things like that, but for teaching purposes, these diagrams are good, give you a better overview. And in the case of iron, we have if it goes into the high spin state, the high spin state has a magnetic moment much higher than 2.2 mu B. It goes to about 2.5. We're going to see these experimentally as well. So, normal means this. Now, when we go back and look at the phase diagram of iron nickel, this is just to show you what range we did the thermal expansion measurements. All up here, in pure iron, we have a Curie temperature which was here, and this is all gamma FCC, and as you add iron, we get martensitic transitions with very broad hysteresis. So you have a martensite start temperature here, finish temperature here. You come into the martensite state. We call that martensite. It's not iron carbon martensite. It's not tetragonal. It's still BCC in this case, but we still call it martensite. Yeah. And then when we go back up, there is this huge hysteresis about 200 Kelvin, which has to be overcome when you come up here. when you are in the FCC state, after this composition, everything is stable. So everything here is face-centered cubic. The INVAR composition, that lies somewhere around 35%. That's around here. And the Curie temperature of the FCC state, that goes down like this. And the nail temperature of FCC iron, you can actually measure by stabilizing films, is around 70 Kelvin. These dotted lines are expected. This has to come down one way or another. This is also going down. It's not measurable. But you see, you have a region here which these meet. You have competing magnetic interactions. And at very low temperatures here, in some of these, you can see that you have a frustrated state because of the competing interactions over here with the antiferromagnet and the ferromagnet. So this we come back to again, and we want to know now what is happening to this. So people have done the same kinds of calculations, not only for the pure elements, but also for alloys, provided that the alloys were not too complex. You cannot just calculate any composition. You calculate stoichiometric compositions where you can define a good unit cell, so it's good for the calculations. If you go off stoichiometric, then you have to define these huge supercells so that you can perform a calculation, but then the computing time takes too long. So to simulate, in those days, the iron 65, nickel 35, instead of 65-35, you take 75-25, which is also close to the INVAR composition. And when you look over here, this is this particular alloy over here, somewhere in between here, and you find these crossing effects of the general lattice curve also in those compounds. So this is also descriptive of the alloy. So what do we see here? We have an iron nickel. That's again our volume, and this is the binding energy. And we see here that at equilibrium in this particular alloy, we have a high spin state. And if we can compress this, if we go to smaller volumes, then we can go into a low spin state in this thing. So we have a discontinuity over here, and the energies involved between this low spin state and the high spin state is again in the order of 10 millielectron volts. But what has now happened? Things have changed around. Let's go back to this. You see that the antiferromagnet, the presence of the antiferromagnetic state here kind of pushes this curve to the right. You can also look at this as an anharmonicity. So what you have is, instead of a curve like this, which would show a regular anharmonicity and a regular expansion, the presence of this curve, the fact that it is more outside, tells you that you can swing the atoms out more further, giving rise to a larger thermal expansion. In this case, you see that it is the high spin state that is of lower energy. And the low spin state, it is here. The curvature of these curves gives you the bulk modulus, the second derivative. So that if you look at this all together, you find that the anharmonicity is not towards larger volumes, but it is towards smaller volumes. Yeah? So this means that we can make this thing smaller than it should be. This difference here, as I said, is about 10 millielectron volts. So if we start increasing the temperature, we're going to have an effect of coming more and more towards the low spin state. So we can go to smaller volumes. In the other one, it was going to larger volumes. So what is happening then? The system is expanding normally. Okay? It has a normal thermal expansion. But then as you increase the temperature, if you're going more and more into the low spin state with increasing temperature, which is at a smaller volume, then this effect is counteracting the normal expansion. Okay? So the magnetism is taking you from a high magnetic moment, high volume state, to a low magnetic volume, a low magnetic moment, low volume state at a higher temperature. And this is counteracting the regular thermal expansion. And this is precisely what the INVAR effect is experimentally. If this compensates fully, then your thermal expansion is zero. And that is exactly what we see. Now, it was not until 1926 that people had started realizing that magnetism was involved in this whole process somehow, because the Curie temperatures were going down and these effects were coming up and so on, as we had seen in the phase diagrams. And but after these calculations were available, then it became more and more evident of what was going on. Now, let's look at the experiments, and we'll come again to back and forth to these diagrams to understand what our experiments, how our experiments are related to these diagrams. Experimental evidence for the stability of Fcc iron. Okay, it runs under this heading. Now, if we take Fcc materials, iron manganese, that's face-centered cubic, iron nickel, iron platinum, ordered, disordered, iron nickel. And if we plot at low temperature the composition dependence of the lattice parameters, what do we see? We see a group of materials here. Those are the iron platinums. When you extrapolate the lattice parameters to 100%, which is X, meaning this is pure iron, then you come to a point which is this. You take the iron-nickel system, which shows an increase of the lattice parameter with increasing concentration up to about this point before it deviates. And if you extrapolate this, then you come to the same point. So basically you're going from here, from nickel-rich to Fcc iron, okay? So it's increasing. And then you look at these two, iron manganese and this particular material. Now this and this, both of them are ferromagnetic. These things, this and this, they are antiferromagnetic. And when you extrapolate the lattice parameters, you come someplace else. So you have a volume which is stabilized at a higher volume than for the antiferromagnetic materials when it's extrapolated from the antiferromagnetic materials. So in this case, Fcc iron has a low volume state, and here it has a high volume state. If you look at this deviation, and with some fantasy, you can perhaps say that, okay, as of the INVAR composition, it is going down again. So as you approach iron, it behaves more like the antiferromagnetic side, and you come to these 2 points. This was the first recognition that iron could come in two states depending on which environment the Fcc iron was. this was the simplest evidence. And then people grew iron films on various substrates and looked at iron again in various environments. And here, in such a manner, you can also plot the atomic volume dependence of the hyperfine field in the case of Mössbauer experiments. So this is a collection of the results of Mössbauer experiments. You have here a substrate which is copper with a certain lattice parameter. You grow Fcc iron on it. And then you can make other substrate. You can add a little bit of gold to copper so that you increase the lattice parameter, and you put iron on it again. And what happens is that the hyperfine field, which is proportional to the magnetic moment that you have, all of a sudden jumps from an antiferromagnetic case to a ferromagnetic at a particular atomic volume. This is the estimated hyperfine field in iron, in gamma iron. And these here, you can also make an alloy with a very small concentration of iron in copper so that you have coherent precipitates. Coherent precipitates meaning that iron is in the Fcc state as with copper. But this happens only when your particles are very, very small. And when you do experiments on that, you get results which are similar to that. At these, other than bringing the Fcc iron onto substrates, you can also check and see what Fcc iron is doing in other environments. This here is iron 4 nitrogen. Iron 4 nitrogen is basically Fcc iron with a nitrogen atom in the middle. Okay, the electronic properties are a little bit different, but it has expanded the lattice so much, and if you look at the hyperfine field, you see that it sits over here. I haven't labeled this for some reason, I forgot, but this was another material where you had also Fcc, Fcc iron in a certain environment. So this is another experimental evidence that you have the antiferromagnetic to ferromagnetic transition in iron. Now, you may already realize, and this was the intention, that when you look at iron-based Hoistlers, in iron-based Hoistlers, again, depending on the distances, you can change a lot of the magnetism. You can get antiferromagnetic or ferromagnetic iron-based Hoistlers as well. And you can get antiferromagnetic Fcc steels, and you can get ferromagnetic Fcc steels. It's just a question of changing around the volume and putting the thing into high spin states or low spin states. When we look at the overall expansion of iron, we showed that it had a very, very large thermal expansion coefficient. But if you just take iron and measure the thermal expansion, you'll see that the length will, or if you connect that to the atomic volume, it will increase and increase and increase until it gets to the Fcc BCC transition, where it suddenly drops. It goes into a more close packed state, and then it goes up, and then you're back in the BCC state. So actually, basically, these here, they join. You can join these two, so you have the thermal expansion in the full temperature range. You realize here that the thermal expansion, if you calculate the thermal expansion coefficient from this, then you lie on the general expansion curve. And then you look at Fcc iron. It has a steeper slope. What else do you have? you can measure in antiferromagnetic gamma iron the atomic volume by stabilizing it. And then it is also possible to check the room temperature value of FCC iron from such extrapolations that I showed you on the first curve. You can do this at low temperature or at room temperature. So you have these points over here. So somehow these points and these points have to join. And this, in overall, gives you a very large thermal expansion coefficient. And I have to go back to show you what I didn't show you in the beginning. Yeah, here we are. I said never mind this curve in the beginning, okay? Now mind it. So this is the thermal expansion coefficient of what you measure. And from these various considerations, you can consider a model where you have transitions from the low spin state to the high spin state, of the antiferromagnetic state to the ferromagnetic state, as excitations, and that gives rise to a maximum that looks like this. It's a Schottky maximum. And you can fit, by knowing what the thermal expansion coefficient should be, by considering these metastable states, you can construct the thermal expansion coefficient of gamma iron in the full temperature range. Okay, so that's basically this over here. Another point that tells you why you should have a maximum is that if you calculate the average thermal expansion coefficient of this whole thing from here to here, that turns out to be larger than the thermal expansion coefficient that you have here. So that this thing has to go through a maximum somewhere. Now let's go to something which we hopefully learned a little bit yesterday. The neutrons. Yeah? Winfried Petri always says, neutrons always tell the truth. Yeah? So let's go to the truth. So remember I showed you some polarization analysis experiments yesterday, how the spins come, they flip and you do all sorts of analysis, and then you can extract the magnetic part of the scattering, and depending on these features, then you can say you have long-range ordering, or you have short-range antiferromagnetic ordering, or short-range ferromagnetic ordering. Now, these are all neutron diffraction experiments that have been performed on that instrument that I showed you yesterday. It's actually a funny story. I mean, when I was doing these experiments, I needed samples that were about that big and about 1 centimeter in diameter, and to correct for some scattering conditions like absorption, then they had to have different thicknesses so that you have the optimum scattering conditions. And I took these samples there, and we started measuring quite a long time. The proposal got through, but in the proposal they probably didn't read the fact that I'm going to measure FCC iron, and we're going to see that the magnetic moment is going to increase with increasing temperature, because we have low spin to high spin transitions. And there were people there that thought I was crazy and things. But we ran the experiments, and the results turned out to be very interesting. This went on over several beam times, of course. So we have here alloys of iron nickel of varying compositions. Okay? 65, 75, 80, and we have here 9010, which is almost the composition of pure FCC iron. I was limited by my furnace, which I had to build for these experiments at that time. I couldn't reach the pure FCC iron region, so this was the limit of the furnace. Now, what do we see here? We see here a forward scattering, okay? And what did we say yesterday? The forward scattering is an indication that we have ferromagnetic correlations. Just in between, I'd like to say here that we have here in a pure paramagnet where you would have pure local moments, which is very unlike the case in metals. Then above the Curie temperatures, your moments are disordered and period. That's finished. Okay? There are no correlations. The correlation length is nothing. There is no correlation. So you wouldn't see forward scattering, you just see a straight line. Okay, in that case. In metallic ferromagnets or antiferromagnets, above the Curie or Néel temperatures, the atoms still know each other. The spins still know each other to a certain extent on a short length scale. This is because your magnetism is dominated by the d electron. And the d electron moves around. It doesn't move around as much as the s electrons do. They move around about 1,000 times less than the s electrons, meaning that the d electron spends most of its time around the atom, but then it hops to the other one. Okay? So while hopping to short distances, it has to carry some kind of information along with it to the next one, saying I'm ferromagnetic, or there are a couple of ferromagnetic that fluctuates and things, but you have regions always that are fluctuating, which show the presence of some kind of a correlation of a very, very short distance. They're not ordered, but they tend to be, they would like to be ordered. So that's why you have this forward scattering peaking at Q equals 0. Now, here in the case of iron 65, nickel 35, what do we have? We start measuring at around 600 Kelvin. We increase the temperature. You see that the forward scattering is decreasing. If you assume this to be something like a Lorentzian or something, and you fit this and look at the half width, you can say something about the correlation length. And if you integrate it up to the zone boundary, or the Brillouin zone boundary, then you can say something about the magnetic moment. Not precisely, because that depends on in which energy range your instrument is working and things, but you can actually, at least qualitatively, and by some calibrations, you can try to see what the magnetic moment is doing as a function of composition and as a function of temperature. You go to the next one, iron 75, nickel 25. This was the composition where the thermal expansion was crossing the general lattice curve. So you were seeing somehow both kinds of effects in that particular system, both the anti-invar and the invar effect. Again here, as you increase the temperature, you see a variation of the forward scattering. It weakens as you increase the temperature, which is an expected thing. And the weakening, if you kind of estimate the magnetic moment, you see that here in the x equals 35 sample, it decreases with increasing temperature. Here it also decreases. And as you come to more and more iron-rich compositions, this decrease becomes weaker. And you come to x15, what happens? There's practically no change. There's nothing changing there. And at s equals 10, this is the punchline of the whole thing, actually, is that your moment is increasing, or your magnetization is increasing with increasing temperature. So this is where the neutrons tell you the truth.